Welcome to another video explaining the universe using the particle model. Today's video is about the hydrogen spectrum. This is the thing they use, the event they use to determine whether a star is moving away from us or towards us. And what you get with a star that's burning hydrogen, and you know it's burning hydrogen because it gives you this spectrum, and it's an absorption spectra. You have a hot interior, which generates all the frequencies, and a cooler atmosphere. And as all that light comes through the surface of the sun, the vibrating atoms of hydrogen block the transmission, and you get what's called an absorption spectra, a red, blue-green, blue-violet, and violet. And here's a simple example now, but this is an emission spectra, something that you would do in the lab to do some testing. This is a gas discharge tube containing hydrogen. It's sent through a slit, possibly some other filters, in this case through a prism. And the prism splits it out, and this emission spectrum, you get red. It's not a dark line, you actually see the color red, blue-green, blue-violet, and violet being displayed. Well, they actually have an instrument called a spectroscope just for this purpose. And this is a video of this gentleman is teaching a class. And the class, this is a lab, and the students are to mark the spectral lines that they see of gas from a hydrogen gas discharge tube. You look into here and you'll see a scale. There's a scale back here in nanometers. And here's the red line, and there's the blue-green line, and blue-violet, and so on. He was teaching that earlier. And then he opens it up, and he shows how it works on the inside. Light source comes in over here. It goes through a slit. It's a diffraction grating here, which sends the light back to the scale, which is over here. This light is, just push this to light the scale so you can see it clearly, and you look in here over the light into the scale, and then you can see where the lines are. It's a spectroscope. Well, a diffraction grating diffraction is made often with clear glass and lines drawn on the glass and light shining through it. In this case, it's a lot more mechanical, and the light coming in, this is white light, and the white light has a normal angle of incidence, angle of reflection, and you'll see white there. But it'll diffract at different orders because you actually have multiple ones of these. This is very small, very tiny. Many of them, the light spread over all of these, so you kind of get 1, 2, 3. Here you get the fourth rainbow. And as you go out, they tend to overlap. The really clear one is the one right here, and actually the one here on either side of the white line. These are both very clear, and these tend to overlap. So the spectroscope tends to look at it from that point. Now here's a real emission spectrum, and you can see that this is recording the strength of the light at different wavelengths. Actually, this is an angstrom, but the width of the red is really shown here by the width of the detected signal, there's a little red line here, and there's the blue-green, and maybe this is the blue-violet. Hard to detect the other one. It's hard to see that. But the interesting point is you get a lot of stuff, and visually you can see it here. You get a lot of light in a lot of different areas, and it's a challenge to pick out some of the smaller ones. These two main ones are fairly easy. Well, the standard model explanation then draws a model of the Bohr model of the hydrogen atom, and here's the nucleus. This is level 1. It's labeled as ultraviolet, and here's I guess this is you got ultraviolet and the rest of the colors. Oh, infrared is up here. But the atom doesn't have that many shells. You normally see in a more complex atom a lot of circular shells, all spaced nice and even, not with this kind of distribution. But what's interesting is the reason this is drawn this way is because of the hydrogen spectral lines. So what they did was they took the same spectral line, they flipped it over from the previous slide. Now the red is here, and then the blue-green, blue-violet, and violet. This is what it should be saying. And here's the hydrogen atom, and here nucleus, and here's the electron orbiting. And what they're really saying, and I'll show this in a bit, is that when something comes in and bumps this, moves it up here, and then when it falls back down here, it'll emit a red spectra, a red photon. So what they've done is try to graphically show that the energy involved with the transition of the electron up and back. Interesting point is that if you're going to move an electron from here to here, you actually have to slow it down. I mean, if you take it literally, it has to slow down to move up, and it has to speed up to go back. They don't say that, but in normal orbiting, the further away it is, the slower it has to go if it's going to maintain an orbit. Whether it maintains an orbit or not, I don't know, but that's how they got this particular placement of the lines, is from the spectra itself. Well, our TPM rejects the extra levels of the Bohr model. You know, yeah, it's got this one, but this is not the way the particle model explains light. This is the way it's been explained, and I've used this diagram any number of times, where they say that a particle comes in, excites this hydrogen atom, it moves up to a higher level. When it falls back, it releases energy in the form of a photon. The frequency of that photon is based on that extra energy divided by Planck's constant. And that's why in one case it's red and in something else is because it depends on how high a level it jumps. That's not the particle model explanation for light being generated from a hydrogen gas. Previous video I've done titled The Candle, and this is explains the light generation based on vibration. This is the candle, which has blue at the bottom, red at the top, and red, orange, and yellow and white throughout. This particular this is my video. That's a link to my explanation. And what you have is you have the cooler temperature down here and the hottest temperature up here. Cool temperature causing the vibration back and forth, very small, making blue light, And when it's very hot, it moves very far, and it takes longer to move back and forth, and therefore you have a wider wavelength, which is red. Vibrating atoms is what does that. And that's what happens in the gas discharge tube. The model for hydrogen in the particle model is there's one N1, one G1, one level normally. G1 can get trapped. If another G1 comes along, it can take a different orbit, get trapped, and then I don't know how, whether it's the same plane or a different plane or what. I don't know that. Just that it can get trapped, or an existing one can be released, can get hit and can be hit and leave. This is moving at high speed. You hit it and you bounce it away. It's going to go away. Why would it go up to a certain point, hang there, and come back down? It could, but it's much more likely that if you hit that target right there, that G1 particle, it's going to scatter and move away. That's the particle model would be our explanation. Now here's an interesting picture. It's really a sound wave, acoustical longitudinal wave. The reason I liked it is because here I could say that this is a vibrating atom. And here's a stream of G1 particles going through the gas discharge tube. And when that pushes forward, it pushes the stream out in a clump. And you can see the clump as it moves out. And the rate, the time it takes for this to go back and forth determines the wavelength. That's the TPM explanation of the spectrum. Now, this is the emission spectrum, not the absorption one, but they use the absorption one to say that when they get light from a star, and this bar is moved to the right, that's called redshift, when it moves to the right, and this correspondingly moves to the right, and it's in the wrong place, then the star must be moving away. If it's blue shifted, then these bars move to the left, and you'll see them here and here. That means the star is coming closer. Andromeda Galaxy is one galaxy where all the stars in the galaxy are blue shifted. That's one of the reasons we know it's coming towards us. But that's what the red shift and blue shift is, because from the stars, it doesn't appear in the same place that it does when you do it in the lab. And this is clearly in the lab because this is an emission spectrum, not an absorption spectrum. Yeah, so we reject this and reject this, and we use the vibrating atoms as the source of the frequency that causes the emission spectra to happen the way it does. My name is Bobby Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.